All right. So let's take a look at this question. So what did I say we should do first? I was,
Freebody diagram.
whispering in some of your conversations that maybe a free body diagram would be a prudent choice. So tell me about some forces acting on that ball that's hanging. What you got?
Force of the earth.
The force of the earth. And which way does that one pull or push?
Down.
Straight down, right? So we're going to go ahead and draw that force. I'm going to make it orange because I like orange.
No, it's hanging off the ceiling.
The force of the earth on the object, Fg. Okay. Any other forces acting on that object?
So force of tension of string 2 and of string 1.
Yeah, does that make sense? You got two forces of tension, yeah? So you got a tension force pulling in this direction. So the force of string 1, or string 2, excuse me, on the object, I'm going to call that Ft2. And I've also got a force of tension going up like this. The force of string 1 on the object, Ft1. How are we doing so far? Okay. Now what? Every time you do a forces problem, after you draw a free body diagram, what's the next kind of step? Yeah.
To find what the forces are equal to, so like FG is going to be
Okay. So you can absolutely figure out what the forces are going to be equal to. Yep. So you could say, for example, that Fg, we know that's the mass times the acceleration due to gravity on the Earth, right? So you said 0.5 kilograms times negative 9.8 meters per second squared, I'm assuming is what you did. And when you multiply that together, you got? Units, newtons, yep. You could say, or you could say kilogram meter per second squared. If you feel about Isaac Newton like I do, then you might want to just say kilogram meter per second squared, and that's 100% fine. I just get lazy, so I have these kind of mixed emotions about, how I feel about Isaac Newton versus how much I want to actually say every time. So negative 4.9 newtons. Fantastic. Thank you. Now what do I do?
You can find the other two forces, which we know have to equal 4.9 because F net is 0.
Okay, so back me up because I was kind of with you, but I'm not 100%.
F net's 0 because the ball's at rest.
Okay, so let me write that down first. So F net, the total of all the forces acting on the object has to be 0 because why? Because the object is at rest, so it's not accelerating. Everybody happy? So all of those forces have to add up to 0, and you've got a negative 4.9 pulling this way, which means that these two have to add up to 4.9. But are these both pulling straight up? They're not. They're pulling at funny angles, aren't they? So that kind of throws a little bit of a wrench into things. So what might I do? What were you going to say, Chris?
The force in the y direction of those two has to equal 4.9.
Okay. So we're going to break these up into pieces, into components, okay? So you have done this already. You did this when we launched projectiles at an angle, right? You had an initial velocity that was at an angle, and you broke it up into an x part and a y part. We're going to do the same thing for the forces. No big deal. We've got this. So I'm going to take this green one to start, and I'm going to draw it kind of down to the center. And I'm going to break that into two pieces. One that goes straight up and down. I'll call that F. I'm going to make this bigger so you can see it. Ft1 in the y direction. And then I've got part of it that's going over like this. Ft1 in the x direction. So I'm kind of writing that over. But does that kind of make sense? Yeah? Now, these angles are a little bit funny. This says that it's a 30-degree angle. Is there a 30-degree angle in this triangle?
Yes.
Yeah. Where is the 30-degree angle in this triangle? Right here. Does that make sense? Okay. So using your geometry skills, this dotted line here and the orange line, they're parallel, right? It's like a transversal. Do you remember this from geometry class? Right? And if you've got opposite interior angles, yeah, do you remember? Yeah, right. I used to teach geometry and I miss it. So I just have to relive it sometimes in my physics world. So this is my 30-degree angle. Is that okay? Let's do the FT2 one since we're here and I've already, you know, kind of made this really, really big so we can see it. So I'm going to draw this one down here like that too. Oh, I drew it. I kind of wrote this too big. Let me make that a little bit smaller. So FT1Y, because I want to do the same kind of deal up this way. Oops, a little bit higher. Maybe there we go. So this is FT2Y. And then I've got the same kind of deal going over like this. FT2 in the X. Is that okay? What's wrong? Were you upset with something? Josh, what are you upset about? It's like, I'm not upset about it, but I feel like maybe you are. Did I draw my triangles differently than yours? Or? Are you sure?
Yeah.
Okay. I don't want to make you upset. So is there a 60-degree angle somewhere in this? Yeah? Where's that 60 at? Right here as well, right? Okay. All right. Okay. What am I going to do with all this information, friends? Are you stretching? Okay. I just want to make sure I wasn't ignoring other hands. Go ahead, bro.
Are you going to use trig to find the hypotenuse of those triangles?
So I could, yeah. So let me ask maybe so you're kind of thinking like, you know, that 60-degree angle and you kind of see these two. So there's definitely some trigonometry involved. Is that kind of what you mean?
I mean, you know one of those values, right? When F2y be 4.9.
FT. So this orange one plus this orange one. Is that what you're asking?
Yeah.
So those two. So let's. I think what you're wanting to do is writing some FNet equations. Is that true?
Yeah.
He wants to write FNet equations, but not saying it. Are you confused or are you happy-ish? Okay, please, because I really want you guys to get this. So like, talk to me if something's not making sense. FNet in the y direction. Let's write down all the things that are acting in the y direction. What's acting in the y direction? Gravity, Fg. That one's negative. What else? I'm just going to write F2 because I'm lazy. Is that okay? And F1, Y? And these are both in the positive direction. What do those add up to? 0, because it's not accelerating in the y direction, right? It's not going up or down. Not only is the net force in the y direction 0, what else is 0? How about the x direction? Is it 0 also? Yeah. If you can write that the total has to be 0, then in each direction it's 0 also. So Fnet in the x direction, F2 in the x, plus F1 in the x also equals 0. F2 is in the positive direction. F1 is in the negative direction. Is that okay? We know a lot of stuff here. So now I think, if I'm right, though, if I was understanding what you were saying, you're saying that we could write like FT1 in the y direction as like a cosine thing related to this?
Yeah, but that's not right, is it?
You can. That's not wrong. But you're
No,
second guessing yourself.
I thought FGY was going to be like the opposite of FG.
Oh, I see.
Yeah.
So these two added together will be opposite of that.
Yeah.
Yeah.
I was just thinking of it like normal force, but there's no surface.
Right. Yeah. Any inclination as to what we should do next? There are lots of different ways to approach this question right here.
5 sine 30 plus 5 cosine 60. Or 4.9.
Yep. So wait, hold on. What did you say?
4.9 cosine 60 plus 4.9 sine 30.
Why are you saying 4.9?
That's the force of gravity.
So that would go in here.
Yes. I've lost myself.
That's okay. I'm going to make a suggestion. You ready for a suggestion? Yeah? Here we go. This is my suggestion for you. I'm going to use this one right here. This is a suggestion from somebody who's done a problem like this a bunch of times. Okay? And sometimes I try and chase down this F net Y, and it always is a big pain in the butt. Not going to lie. F2 in the x direction is this here, right? Which is just F2 times the sine of 60. Are you with me there? I'm going to write that down. Ft2 times the sine of 60, and that's positive, plus Ft1 in the x direction is just Ft1 times the sine of 30. That's in the negative direction. What does that have to add up to, friends? Can you tell me which one of those is bigger now? Do you know what the sine of 60 and the sine of 30 are? And or do you have a calculator that can tell you? Can you figure out which one of those is bigger? Yeah. If you're like, I don't know, get your calculator out. Play with it real quick. I want you to try it. I want everybody to feel okay about this. I'm going to pause for just a second and let you figure it out. So what are you saying?
So if the sine of 60, does that mean that but then how would that be 0 if the sine of 60 is going to be or
So what is the sine of 60? Plug that into your calculator. What is it?
0.8660254.
Well, that's a lot of sig figs. Give me, round it to the nearest hundredth.
0.86.
87, whatever.
Or 87.
Okay. Minus Ft1. What's the sine of 30?
0.5.
It is, yeah. That one's really easy, isn't it?
I think I like that one better.
Yeah. What do you know about Ft2 as compared to Ft1? Which one's bigger? Ft1. It's got to be bigger. Does that make sense? Okay. Does it matter how much that object weighs or has how much mass it has? No. Given those two angles, Ft1 will always be a bigger value. So you could say Ft2. You okay?
Yeah.
I'm just going to write it out for our friends at home in case they get confused. Right? So you could find a ratio, right? 0.87 over 0.5. Yeah. So Ft2 is bigger. Yeah? How are we doing? Are we okay? Was that kind of chunky? Kind of hard? A little bit weird? Yeah? The more you practice these, the better. I think that there's at least one of these on the homework. Yeah. Yes?
So do we have to worry about F not Y in the y direction?
I don't know. Do we?
I don't know.
One is.
Well, did we come up with an answer?
Yeah.
And did we have to worry about F net Y? There's your answer. There you go. So the answer is no, you don't. Now I'm gonna jump on Lauren's question here just to help because sometimes you do need to, right? And so this is the deal with these forces problems is that every single forces problem is a little different, right? And so you can't just there's not like an algorithm like you do this and then you know that you don't have to worry about this or worry about this. These are the rules that I would tell you. Always draw a free body diagram. If you have forces that are going in funny angles, break them up so that everything's perpendicular to one another, right? And then write down your F net equations. And then in general, look for, in a case like this, look for the thing that's simplest to deal with, right? And see if you can jump that way. Sometimes you can't, but once you've got the free body diagram and you've got your F net equations, then you can just kind of run and go. Does that make sense?
Yeah.
Go for it. So if I was reasoning this through and kind of like trying to write down an answer, is that what you're saying? My reasoning would be that the ratio of 0.87 to 0.5 is greater than 1. Does that make sense? And so then my ratio here has to be bigger than 1. My Ft1 over Ft2 would have to be bigger than 1, algebraically. Does that answer your question or no? And you can say no. Is that it? Kind of. So let me go further. So if I divide over here, so let me divide by 0.5. Okay. And let me also divide by FT2. Those go away and those go away. So I've got a ratio here of 0.87 to 0.5. Plug that into your calculator. And that's really all we care about, right? Say that really loud, Eden, because you're exactly right. It is greater than 1. And if it's greater than 1, that means that the numerator has to be bigger than the denominator. Does that make sense? And in this case, all we care about is which one was bigger. Yeah. Could you figure out how they are related? Yeah. Yeah. I was just reading one of the AP workbook problems that we'll do, I don't know, a couple days. And it said, you will almost never have to do a bunch of math to on an AP exam to figure out what FT1 or FT2 is. But this ratio stuff, that's what they love, right? Is to find out the relative sizes of things, okay? So actually figuring out what FT1 or FT2 is, okay? It matters, and an engineer would really care, but in AP Physics 1, they don't really care. What they really care about is that relative size, okay? And if one thing gets bigger, how does the other thing, how does it change? Okay. Go for it.
So why wouldn't we need the Y values if we're trying to find the total tension on each of the ropes?
So if you were trying to find the total tension on each of the ropes, you absolutely would. But in this question, the way that it was worded and the way that it's posed, all we care about is which one's bigger. Do you see what I'm saying? So it doesn't say what is the tension in each of the ropes.
So does that mean that the tension from Y on each rope is going to be equal?
No, so the tension in string 1 is bigger than the tension in string 2. If they had the same angles, if they were both at 30 degrees or both at 60 degrees or both at pick any degree, then the tension would be the same. But because the angles are different, the tensions are different. Okay?
So if the tension X is greater for string 1, that means the tension Y will also be greater for string 1?
Say that one more time, I'm sorry.
So does that mean that if string 1 has a greater tension than string 2 for the X-axis, so that means it's also going to have a greater tension on the Y-axis?
Yes, I'd have to think about the angles and how the angles affect it. My gut feeling says yes, but I don't want to swear to that because let me think about it and I can answer that. Is that okay? Yeah. Do you have a gut feeling on that? I just can't, I'm not thinking about that right on the top of my head. Did you hear what his question was?
You're right.
I think yes.
Well,
I think yes, but I'm.
the X tensions are equal, right? So it's not.
True. Yeah.
It's not.
Yeah.
It's a
Yeah.
different
Yeah.
scale from the thing.
Right. Yeah. Does that make sense? Thank you. I was like, I'm just looking at this and it's obvious. Thank you. Does that make sense, Keaton?
Wait, how is it? What do you mean the X tensions are equal?
The F-net equation says so, right?
Oh, yeah.
Is that okay? Okay. How are we doing, team? Ready to go back to new question? Get another one? Yeah. We ended with this one yesterday and we didn't really get a chance to finish it. But I told you that we would come back to it, so here it is. Do you have written down your idea, your answer, your thoughts? Yeah? Are you ready or do you need one more minute to talk? You're ready? Back table right here? Emma's ready? Okay. As long as Emma's ready, we're good, right? She's like, yeah, why not? What'd you come up with? Go, TJ, get us started.
Oh wait, I went backwards. Let's get a reset.
I'm resetting.
Oh yeah, my bad. Okay, D is greater than. Okay, just read it.
You're good.
B equals E.
B equals E.
Yeah.
Okay.
Greater than F equals C. Oh, A equals C.
It's all good. It's all good. Okay, so now we have an answer. Does that match everybody else's answer? Some people's answer? Okay. Explain your reasoning. This is the part that makes it harder, right? All right, go, Chris.
Okay, so D, or the first, that row D
Uh-huh.
is pulling all of the boxes, so it has to exert, it's gonna have the most tension on it, because it's got all the weight on it. And then E and B are both pulling 2 boxes, so they're gonna be less than D, but equal. And then F, C, and A are all pulling 1 box, so they're going to be less than the other 2 conditions, but all equal to each other. So it's 1 box.
Okay, we catch that? How does the acceleration compare for each of those boxes? Same acceleration. So that means that as the mass increases, what happens to the force? It increases. So D, as Chris just said, is pulling 1, 2, 3 boxes, has a mass of 3, the force is going to be, right, 3 times as large. Yeah? Good show. Okay, can we keep cruising? Okay. All right. Mystery box, here it comes. Oh, this is like the mystery box train. 2 boxes are connected by a lightweight cord, setting on a smooth, frictionless table. The boxes, there are 2 of them now. So there's a 10-kilogram box and a 12-kilogram box. A horizontal force of 40 newtons, we're back to that silly 40 Newton force, is applied to the 10-kilogram box as shown in the picture we are going to draw. Okay? So it's to find the acceleration and the tension. Think we can do it? Yeah! The enthusiasm was a little lacking, but I'll trust you. All right, let's go ahead and draw our 2 boxes. So I'm going to do a 12-kilogram box, and we'll do a 10-kilogram box. They're connected by a little cord, and they're pulled on by a tension force of 40 newtons. Says to find the acceleration of each box and the tension in the cord connecting the boxes. I'm going to ask one question here really quickly, and then I'm going to let you work. How does the acceleration of the 10-kilogram box compare to the acceleration of the 12-kilogram box? Greater than, less than, same as. Same? Jason, was that what you said? Why did you say same? They're connected, right? Those 2 are connected. And if you think about what acceleration means, it means change in velocity over time, right? If the 10-kilogram box speeds up from 0 to 4 meters per second in 10 seconds, I'm just making numbers up, the 12-kilogram box is going to do the same thing. It's going to speed up at the same rate because otherwise this one would either lag behind or it would run into this one. Are you with me there? Yeah. So the accelerations, and this is not a trivial statement, of the 12-kilogram and 10-kilogram box are the same. Okay? Special hint, top tip. Why couldn't this just be one big box with a mass of 22 kilograms? I'm going to let you work. There you go. Get started. Okay. So, friends, I want to address a question that was asked to me and also just address some stuff about. So part A says find the acceleration of each box. So we agree that the acceleration of each box is the same as the acceleration of the whole thing. So this green thing is what I would call a system, right? So this is a system. I know, it's always frozen. There we go. A system, which means that we can treat this whole thing as just one object, okay? When we treat something as one object, any inside or what we call internal forces don't matter, okay? We can argue that there are tons of internal forces inside any object, Okay, a lot of, electromagnetic forces and things like that that we don't worry about when we're talking about the object as a whole. So this internal force, this tension that exists in between these boxes does not matter if we talk about the green box as a system and just one object. Okay? If we do that, we draw a free body diagram, because why wouldn't you draw a free body diagram, right? So you've got a gravitational force pulling down, you've got a normal force pushing up. Do we need to worry about the y forces when we're solving this problem? No, unless it asks you to draw a free body diagram, but we like to acknowledge these things. In the x direction, mass times acceleration is the truth. Is the box accelerating? How do you know that it's accelerating?
And the force applied to it is greater.
How many forces are acting on it in the x direction? One. Question for you, because we haven't really talked about this. If you have only one force acting, is it possible to not be accelerating? If the net force equals 0, that means that there's got to be 0 or at least 2 forces. Could it be 3 forces and not accelerating? Yeah, it just can't be 1, right? Because if you only have 1, you can't add one number to get 0. So it's got to be accelerating, and that's because of that tension force on the outside. So you've got the acceleration is equal to that tension force, that 40 newtons, divided by the total mass, which was 22, thank you. Gives you an acceleration of something. What did you get? Fantastic. So how do you do part B then? What is the tension in the cord connecting the boxes? Are we going to talk about it in terms of this big green system now? We're just going to look at one of the boxes. Do you have a preference? I would use this one. Keep it as simple as possible, right? If you look just at that box, just at the 12 kilogram box, you've got gravity pulling down, you've got the normal force pushing up, and how many other forces do you have acting on it? Just one, right? The tension or the force of the 10 kilogram box on the 12 kilogram box. So I'm going to write this as the force of 10 on 12. That is a tension force, and that's the one we're trying to solve for. Okay? F net in the x direction equals ma. Is the 12 kilogram box accelerating? Yeah. Do you know what the acceleration is? Because you just found it, right? Yay for us. Is equal to this ft that we're trying to figure out. Okay? And then you can solve, bam, for ft. Did you get a value yet, or you still need to work on it? 21.8? 21.6? Okay, I don't know for sure. I don't have it in front of me. Something like that? How are we doing? Okay-ish? Yeah, I'm gonna repeat what Eden said, and I'm gonna add something to it. Is that okay? I'm not trying to point it about that way, but it's a very good question. She says, so when you're dealing with the 12 kilogram box, you don't have to factor in the 40 Newton force, and the answer is no. And in fact, you don't want to, because the 40 Newton force itself, that force is not acting on this box. Are you with me there? The only forces acting on the 12 kilogram box are the gravitational force on the 12 kilogram box, the normal force on the 12 kilogram box, and the force of the 10 kilogram box on the 12 kilogram box. Those are the only 3 forces. That 40 Newton force is not acting on this, right? This is the only thing. Yeah. Does that make sense? So it's a very good question. It's an important one to ask. Okay. Are you ready for one more? Say, bring it. We got this. All right, here you go. More ranking, more fun. Holy cow. Yeah, this is a good one. This will be a good thinker. This will get us ready for tomorrow. Tomorrow, pulleys come in. Yay! In each case below, so let's look at this together, friends. In each case below, a box is sliding along a horizontal surface. There is friction between the box and the horizontal surface. Okay, I see some angry faces out there, but yay. The box is tied to a hanging stone by a massless rope running over a massless, frictionless pulley. The reason that we call these things massless and frictionless is so we don't have to do calculus. Okay? Okay? Well, someday down the line you'll do that, but not in here. Okay? All of the cases are identical except for the initial velocities of the boxes. Okay? So all of the setup is the same. So all the blocks are the same. All the rocks are the same. Okay? You'll notice that some of the velocities are going to the right and some of them are going to the left. Before you begin ranking things, you probably want to draw some Freebody diagrams, right? And it's all the same system. I'm going to let you chew on it a little bit. Draw a picture. Draw some forces. You've got this, you guys. You can do this. This will prove to me that you get this stuff. Go for it. There's a lot of good physics in this problem. Holy cow.